the sentence really gives you the equation. It says the mass of the square sheet of glass is directly proportional to the square of its length. So the mass is directly proportional to the square of its length. So to the length squared. I always write my L's in cursive because otherwise they look like ones. So mass is equal to K times the square of the length. It was confusing what they were giving you because they said a 30 centimeter square sheet. So were they giving you a length or were they giving you an area there? But because the unit wasn't squared, I determined that that was a length. Okay? So we want to say, it says given 30 centimeter long square sheet, so that would go here, has a mass of 900. We can use that to determine K. So I get 900 equals 900K. So K equals what? 900 equals K times 900. Yeah, K just equals 1. Divide both sides by 900, and you get K equals 1. So that means the equation is just y equals 1x or y equals x. Honestly, a lot of people find it easier to look at y equals 1x because y equals x is so straightforward, it can be confusing. You can write it as y equals x, though. That's the most simple way to write it. All right. Or in this case, instead of y equals 1x, it would be m equals l squared because the k is 1, or 1l squared. Okay? So it says find the mass of a 50 centimeter square sheet. So mass is equal to 1 times 50 squared. What's 50 squared? 2,500? Yeah, okay. And then don't forget your unit in the end. All right, so today we're going to talk about composite functions and we're going to talk about inverse functions. Those are both things that you learned about in Algebra 2 as well, but of course we do things more in depth here. Okay, so they have interesting ways of defining functions. They're saying f such that x goes to f of x and g such that x goes to g of x. They're just defining two functions, f and g. The composite function of f and g will convert x into f of g of x, which means you put x into g, and then you put the answer to that into f. The way they write it, though, it looks like fog, right? That little O there means of, so it's f of g. If you find fog difficult to look at, you can always rewrite it like this. F of g of x. Okay? All right, so usually f of g of x will give you a different answer than g of f of x. And the one case where it doesn't is when they're both going to be x, and that's when you have inverses. But we're kind of skipping ahead a little bit. We're just going to practice doing some composite functions first. So when you see this, it means we're putting function g into function f. The first function is your outside function. So what I do is I take my function f, which is this one, and I replace the x with parentheses. So do you see how I took my first function f, and I replaced the x with parentheses? Now inside the parentheses, I'm going to put function g, and function g is 3 minus 4x. And I use the two colors just to show you how I'm putting function g into function f. There are different ways to think about the setup, and if you have another way that works for you, that's okay, but it should look like that in the end. Okay? All right, and then we're just going to simplify. So I'm going to distribute that to 2 times 3 is 6, 2 times negative 4x is negative 8x, and plus 1. And then combine like terms. Negative 8x stays, and these two combine to give me a plus 7. So this one starts with function g. So you're going to take function g, and instead of the x, put a parenthesis. So 3 minus 4 times something. And then inside the parentheses, we're going to put function f. So that would be 2x plus 1. Okay? The negative 4 distributes, and the 3 comes down. So 3 minus 8x, and then negative 4 times 1 is minus 4. And then combining these two like terms, I'll get a negative 1. I'll write my negative 8x first, just because I'm writing in standard form where you put the variable with the highest exponent first. However, it doesn't say your answer has to be in standard form, so if you wrote negative 1 minus 8x, you're also right. Any questions? Yes?
So it went to negative 1 because we combined the 3 with the negative 4?
Well said.
Okay.
All right. In this case, in example 2, we're substituting numbers into these composite functions. There's really two ways to do this. You could do exactly what we did and then put negative 1 into the composite function. Or, I'm going to show you a different method just because this is a different problem. What you could also do is you put negative 1 into the inside function, and then you put that answer into the outside function. Okay? So negative 1 into f. So negative 1 goes into function f, and then that answer goes into function g. That's what I'm going to show you. But if you don't like that, if you're like, Ms. Burrell, that's just some made up stuff, what you can do instead is just do your composite function like we did here, and then substitute negative 1 into the composite function. All right, so negative 1 goes into f. F of negative 1 is 6 times negative 1 minus 5, which is negative 6 minus 5, negative 11. And then you take that answer and you put it into g, your outside function. So the negative 11 will be g of negative 11. And that's going to be negative 11 squared plus negative 11. All right, anybody get that answer yet? Anybody else get 110? Yeah, good. So we get 121 minus 11, which is 110. All right, so I want you to try f of 0. You're going to take your 0, put it into f, get your answer, and then put that into f again. All right, so I'm going to put 0 into f. So I'm going to have f of 0 is 6 times 0 minus 5, so I get negative 5. And then I'm going to put negative 5 back into function f. Again, 6 times negative 5 minus 5, which is negative 35. All right, the outside temperature at an altitude A kilometers above ground in a particular city is T of A equals 25 minus 6A degrees Celsius. The altitude of an airplane T minutes after taking off is A of T equals 12 minus 60 over T plus 5 kilometers. Find the composite T of A and explain what it means. I'm going to give you a minute to think about that before we go over it. I want you to think about what would it mean to do T of A? What would be your input and what would be your output? All right. So this is T of A. What is the input in function A? What is the input in function A? It's A of what? Little t, right? What does little t stand for?
Time.
Time. So time goes into function A, right? Function A goes into function t. And what does the big T stand for? Temperature. So what we end up with when we do function t of function A is an input of time and an output of temperature. So it gives temperature based on time. It just kind of takes that altitude out of the equation. All right, so let's do the composite function. Your outside function is t, so I'm going to write this function with parentheses instead of the a. Remember that degree C is a unit. That's not a variable there. Okay, so it's just 25 minus 6a. So it would be 25 minus 6, and then put the parentheses there instead of the a. And then for a, you're going to put in 12. Yeah, minus 60 over t plus 5. And then, yes. Then distribute. And then combine your 25 and your negative 72. Okay. So I'm going to stop there. Did anybody get a common denominator and combine them into one fraction? That would have been cool, but you don't have to do it. I'm going to stop there. Okay, so that is your function t of a. Yeah. All right, what questions do you have before we go to the... All right, inverse functions undo each other, so it's telling you that the inverse of addition is what? Subtraction. And the inverse of multiplication is division. Okay. So if a function has an inverse function, you write it as this, f to the negative 1 of x, and you never say it that way, it's just the way it looks, because actually raising something to a negative 1 exponent is completely different from inverse. Math does these things sometimes. It says things that should mean one thing, but they actually mean something totally different. Honestly, I feel like it was kind of something that some people did when they were creating these to make it confusing on purpose. Don't let those things confuse you, okay? That doesn't mean negative 1 exponent. It means inverse of f. It must satisfy the vertical line test to be a function, and then when you graph the inverse, if that also has to be a function, okay? And you can see the graph as a reflection over the line y equals f of x. Has anybody ever done that before? Looked at those reflections? No? Okay, maybe we'll have time to look at that. We'll see. And it's called the identity function, y equals x, because when you find the inverse, it's the exact same thing. This is helpful. If f of x has an inverse, then they switch domain and range. So all the x values become the y values become the x. Let's do example 4 together. So here's our function. The function f of x is 2x plus 3. And so what that really means is y equals 2x plus 3. It says on the same set of axes, graph the function and its inverse function. So the way we're going to do that is just by making a table of values for f and then a table of values for the inverse. So here's our table of values for f. 0 is a really nice one to put in because it's just so easy. And I'm going to put in 1 because that's easy too. All right. So if I substitute 0 into the function, I get 3. And if I substitute 1, I do 2 times 1 plus 3, so I get 5. I'm going to graph those 2 points, 0, 3, and 1, 5. And because I know the slope is 2, I'm going to probably just graph a few more points to make sure I get in the right place. It's actually really hard for my eyes to see this graph. Okay. And I'm going to use a ruler to make this line nice. Okay. So that line is f of x. Remember how I said your domain and your range switches for the inverse? So if I want to find the inverse of this, what I can do is switch the x and the y. So this would be x and inverse f of x. So now 3 and 5 become my x, and 0 and 1 become my y. And I'm going to graph those points. So 3, 0, and 5, 1. And you can kind of follow that pattern as well to make a few more points if you want. And graph them. So I'm going to go back a little bit. Down 1, over 1. Okay, that's my inverse function. So when they say that a graph and its inverse are reflections across the line y equals x, they're talking about the line y equals x that goes straight through the origin on a perfect like 45-degree angle here. So here's my line y equals x. Can you see how the blue line and the red line are reflections of each other over that line y equals x? Right? It's right here, right in the middle. Okay. Personally, I don't have a good enough design mind that I can graph an inverse that way. I have to do more of the technical switching the x and the y. But if your mind works that way and you're good, you can always reflect your line across that line y equals x. All right. So it says find the inverse using coordinate geometry and the gradient. Oh, sorry, I didn't do that one yet. I did this one. On the same set of axes, graph f and its inverse function. Find the inverse function using coordinate geometry and the gradient from part A. So we already know that this function is, the blue function is y equals 2x plus 3. For the inverse function, if I just wanted to do y equals mx plus b, what is the slope of this function, or the gradient? It is 1/2, right. So let's see, where am I going to write this? I'm going to write m equals 1/2. And your y-intercept, often you can't just estimate it, but in this case you can. You really do know exactly where your y-intercept is, because this point has a y value of -1, and this point has a y value of -2, and this point is halfway between. So what would be halfway between that y value of -1 and the y value of -2? -1.5. So your y-intercept is -1.5, and because I wrote this one as a fraction, I'm going to write this as a fraction too, -3/2. There are other ways you can find that. Remember, if you have 2 points, you can use the point gradient form of the line, and you can find your m that way, and you can write your equation that way as well. That was just my little shortcut there. So that means that the equation would be y equals 1/2 x minus 3/2, and written in inverse notation, f to the -1 of x is 1/2 x minus 3/2. That's your answer to part I. Variable interchange is when you switch the x and the y. Sorry guys, I can see that that's a little bit hard to see. Let me see if I can zoom it for you. Raise your hand if you learned how to find an inverse by switching the x and the y. A couple of you did. Okay. Personally, that's not my favorite way to teach it because people forget why it works. The reason why it works is because inverses switch their inputs and their outputs. And that's why x and y can switch like that. But it is a method that they're asking you to demonstrate here, so I am going to show you how to do it. So we're going to do part II. We're going to find the equation of the inverse using variable interchange. So you start with this one, y equals 2x plus 3. You switch your x and your y, so now you have x equals 2y plus 3. And then you solve for y. So to get the y by itself, what do I do? Minus 3, then divide by 2. Good. So minus the 3 first. X minus 3 equals 2y. Divide it by 2. And I get y equals x over 2 minus 3 over 2, which is what I got the other way, right? And then write your inverse notation.
In that case, would there be a hole?
Would there be a what?
A hole in the line?
So holes are created when you have a denominator that has an x in it, but our denominators are just integers.
But you can't like divide 0 by 2, can you?
You can. You can't divide 2 by 0, but remember 0 divided by 2 is just 0. Yeah. But thanks for bringing that up because we are going to be thinking about rational functions soon. All right, so we did parts 1 and 2. We found the equation of the inverse with 2 different methods. C says check that f of the inverse of f of x equals the inverse of f of x, and they both equal x. Why? Why should they equal x? Let's think about this. We take an x, right? We put it into a function. We take that answer, we put it into the inverse of the function. What's the purpose of the inverse? What does the inverse do?
Switch x and y.
It does, but go to the very top of the page. What does it say the inverse does? Very, very top of the page, right under inverse functions. Undo it, right? So you take the x, the function's going to do something to that, give you a different number. The inverse undoes whatever the original function did. What should you get out? You should get out x that you started with, right? You start with x, function does something to it. The inverse is like the antidote. It undoes whatever that function did. You should get x out. And it works the other direction too. If you start with the inverse and then you put it into the original function, you should also get x out. So that's what we're going to do now. We're going to do a composite of these two functions. I get that the notation is weird, but if you get past the notation, we just have two different functions, this one and this one. Oops, this one and this one, okay? And we're going to do the composite function of those. I'm going to use a piece of paper because I'm kind of running out of room. You could feel free to use some extra paper too. All right, here we go. So we need to do f of the inverse, and then we need to do the inverse of f, and we hope that we're going to get x both times. So f of the inverse of x. Start with your outside function and replace the x with a set of parentheses. Then put your inside function in the parentheses. We're putting a function into a function. You got that? Right, at least. And now I'm just going to distribute. So I have 2 times x over 2 minus 2 times 3 over 2 plus 3. These 2's cancel and these 2's cancel. And so I get x minus 3 plus 3, which is just x. So it worked, right? The antidote worked. It brought us back to x where we started. We have to do the other one too, though. We have to do the inverse of f of x. Okay. This time the inverse is my outside function. So I have something over x. Notice the big parentheses instead of the x, minus 3 over 2. So something over 2 minus 3 over 2. I put parentheses instead of the x. Then I'm going to put this function on the inside, 2x plus 3. All right, so when I have 2x plus 3 being divided by 2, I can break that into two different fractions. It would be 2x over 2 plus 3 over 2. So I have 2x over 2 plus 3 over 2 minus 3 over 2. Three over 2 minus 3 over 2 cancels out. I have 2x over 2, which just gives me x. So we put a function into its supposed inverse, and we proved that they're inverses because when you compose those two functions, you input x, and whatever happened to that x got canceled out, and you got out x again, okay? So here's your mathematical statement. F of the inverse of f of x is equal to inverse f of x, which is equal, sounds like Dr. Seuss, right? Equals x. Therefore, 3 dots means therefore, f and inverse f are inverses. Okay? Now, of course, we already found that they were inverses algebraically, but say we made a mistake. You know, everybody can make a mistake with their algebra. Now we have proven that we did it right, and they are inverses. All right, luckily part D is easy. All right, part D asks you, what is the domain of the inverse function? So I invite you to look back at the graph of the inverse of f. What kind of graph did it make? It made a linear graph, right? Does it end anywhere? No. So what would be the domain? So you can write it in interval notation, negative infinity to positive infinity. Or you could use set notation and write that x is an element of all real numbers. Either one's fine, okay? Can I move that? Raise your hand if you're still looking at it. Okay. All right, so for part D, we're just going to write that the domain is either, oops, sorry, up here. You can write it in interval notation like this, or you don't need to write both, just so that you know. Set notation will be all x such that x is an element of the real numbers. One more, guys, one more. All right, so it says consider the function, and notice they have that weird notation, but just think of this as y equals x squared. Explain why this function does not have an inverse function. So I want you to think about that for a moment. You can even graph it if you want, y equals x squared, to consider why it might not have an inverse function. So we said that this function does not have an inverse function because the inverse would not be a function. You can see that algebraically by making just a table of values, or you can even see it graphically because the inverse of this shape, when you switch your x and your y's, gives you this sideways u, and that doesn't pass your vertical line test, right? The vertical line test, if it crosses 2 points, is not a function. So the inverse is not a function. That would be your answer for A. Okay. And then it says, well, what about y equals x squared where x is greater than or equal to 0? Does that have an inverse function? And we said, yeah, that one works because it cuts off all of those extra x's that we're going to give you a different y. So yes, part B does have an inverse function because it's only half the parabola. I ran out of space there. It's half the parabola. So this becomes this shape. All right, so we have no problem with our vertical line test. It says find the inverse for y equals x squared if x is greater than or equal to 0. So just thinking about it logically, what function will undo squaring? Square root. Very good. So logically, we're thinking the answer to C should be inverse f of x is equal to the square root of x. And what's the square root of 0? Still 0, right? Square root of 0 is 0. So it should have the same domain, x is greater than or equal to 0. Let's look at it graphically to make sure that makes sense, okay? So if I take my original points, let's see, 0, 1, and 2, and I squared them, 0, 1, and 4, does it work when I take the inverse and I switch the x and y? 0, 1, and 4, square root of 0 is 0, square root of 1 is 1, and square root of 4 is 2. It works. And then it says to sketch them, all right? So this here is my f of x, and this is my inverse. And so I am going to sketch these points. I'll try to switch back to the marker. The marker wasn't working that great. Okay. So this is 0, 0, 1, 1, and 2, 4. Okay, and that was f of x. And then 0, 0, 1, 1, they share those points, but the next one is 4, 2. And so it curves this way. And that's my inverse f of x. And notice they are still reflections across that diagonal line, y equals x. Let me make sure I didn't forget anything. I think we got it all. All right, we did good in our short class period, but I know that was a lot.